Let's talk about how we can represent lines and planes in three-dimensional space. So I'm going to draw some coordinate axes here, although I'm not going to focus too much on what the coordinates are yet. But 3D coordinate axes, remember the convention is that y and z are in the plane of your screen right now, and x is perpendicular to those and coming out of the screen. It's coming out of the screen toward you, I guess, or whatever. But it's coming out of the screen perpendicular to the y and the z axes. And a line, we know what a line is, right? So a line is determined by any 2 points. That's one way to say it, but I'm going to just draw a line here. So this line here, L, is somewhere in space, in three-dimensional space. It might look like it's in the plane of the screen, but it's possible that it's coming out in the z direction as well. And let's say that on this line we have 2 points. So these are 2 points that we could use to determine the line. Now, there is a notion of something called a vector in geometry, and a vector is just going to be a arrow that connects these points, or it connects any 2 points, but basically the idea is, so this is called a direction vector. The direction vector points in the direction of the line. Now there's two choices for this, right? So there's one direction vector, and it's just an arrow, right? So direction vector is an arrow that points in the direction of the line. So this is very important because the reason here that this is important is because there's no way to write down a slope as a single number in three-dimensional space for a line, right? So slope in 3 dimensions cannot be written down as just a single number. So instead, the direction vector v tells us something about the direction, literally, right? That's why it's called this. The direction of the line, and the direction, remember, is related to slope. So this is like, we don't want to call it a slope vector because it's not slope anymore. There's not slope in 3 dimensions, but it plays the same role as slope of a line plays in 2 dimensions. So our direction vector tells us what way to go from a given point if we want to stay on our line, right? And that's exactly what slope tells us in 2 dimensions. So here's one choice of a direction vector here. I connected from A to B, and I put a little arrow saying go in that direction. Of course, you could reverse this whole thing, right? And you could have the arrow pointing the other way. You could also make this arrow longer or shorter as long as it stays in the same direction. The only thing you want to make sure you don't do is make it so short that it just becomes a single point and it's no longer an arrow. So as long as this is an arrow, then we're good to go. Now, the question becomes, how are we going to describe this direction vector to someone else, right? And this is where coordinates come in. So the coordinates of our points, remember, it takes, in three-dimensional space, it takes 3 pieces of information to describe our points. So this point A is out x, I'm going to label these as x1 in the x direction, y1 in the y direction, and then z1 in the z direction. So it might be like out x1, maybe a little further. So maybe it goes out x1, y1's a little bit, and then z1 is this much. So you'd go out to here, over to here, and then up to here. So this is our x1, this is our y1, and this would be our z1. Those are the coordinates of that point. Now, what I've done there is just made the picture messier, right? But that's the idea of how you describe the point. To get to the point B, you have to go, a different amount. So maybe here's x2, you only go out this far, and then here's y2, and then z2 is this much. Okay, so our point B will give it coordinates x2, y2, and z2. And then the question is, how do we make our arrow, right? How do we describe our arrow? And the arrow goes from A to B. So this vector v, let me change the color. This vector v is going to be describing the vector that starts at A and goes to B. And the way that we describe this is we want to say that this is an arrow. So we change our parentheses for our coordinates. We need to tell how much the arrow changes from A to B, right? What's the change in the arrow from A to B? So basically what we need to do is we need to say, all right, our arrow does all this, right? So we need to give coordinates for the change. So here's the blue, right? So we've got like our change in x, our change in y, and our change in z, and we want to follow that along to get from the initial point of our arrow to the terminal point. And so we need to compute these numbers, right? Delta x, delta y, delta z, these changes. And those are just the differences. And if we're going from A to B, then we want to subtract. B minus A, terminal minus initial. Okay, so that's how we're going to get the components of our vector. So it's always terminal point minus the initial point. And this ensures that our arrow is pointing in the proper direction. If you did initial minus terminal, you'd still get a direction vector, but it would point the other way, right? Point the other way. So in terms of this, our delta, I'll just write it in 2 steps. So we have delta x, delta y, and then delta z. All right. And what is it going to be? Well, the difference, remember, is terminal minus initial, right? So it's x2 comma x1. Notice I put these kind of angled brackets. These are telling us that this is the coordinates of an arrow, the components of the arrow, right? The change in the 2 points. So you just have to do those to make sure that you're telling everyone that this is a vector or an arrow, right? So, and then you just go through and do the rest, right? So terminal minus initial is always going to be the 2 minus the 1, right? So x2 minus x1, y2 minus y1, and then z2 minus z1. And that's going to be the direction vector, like we said, called v, for our line, for this line L. I said the direction vector, it's a direction vector. It's not the only choice, right? So you can use any 2 points on the line to get a direction vector, and they will be sufficient, unless you want to add some other qualities to it, but we're not going to worry about that right now. But so there you go. So there's a direction vector of a line. Now the next thing I want to talk about is, what about a plane? All right, so I'm going to make my coordinates again, and I had my ruler. I didn't like that. So let's just sketch it. So here's our x, y, z coordinates. Well, what's a plane? A plane is like a 2-dimensional analog of a line, right? So I'll just draw a plane here. So you can't really picture exactly how this plane is going, but it's a sheet, right? It's like a plane. And I've drawn it so that it's not too crazy. Maybe it goes right through. Maybe this is a point. We'll call this P on the plane. And we want to be able to describe this plane to someone, right? So number one, we definitely need this point P that's on the plane. And then the next best thing that we could have is a arrow or a vector to tell us about this plane, right? So if I choose a vector that lives in the plane, like this one, is this going to be enough to describe the plane? So I say, okay, I've got this point P, and attached to P, here's a vector. Let's call this vector V, and this vector lives in the plane. Well, that's not enough, because you can imagine if you fix this line, this is just going to determine a line, right? If you fix this line in your plane, you could spin the plane around that line and find many other planes as you rotate. So as you rotate this plane around this line, you could see how there could be many different planes with the same vector v that passes through P, right? So it's not enough. So what you also need is another vector, let's call it, say, W, that goes in a different direction. It doesn't have to be perpendicular, but I drew it so it looks perpendicular. It doesn't have to be, but it just has to be in a different direction so that you get another line. And those two lines together kind of solidify this plane and make it so that this is the only plane that passes through P with these two vectors, right? With these two vectors. All right, but that's a lot of information. So now we've had to give 2 vectors and a point P. We can do better, because if we take up 2 dimensions of our space, of our 3-dimensional space, with these 2 vectors V and W, we've made sure they go in different directions, right? So they take up 2 dimensions. Then all that's left is 1 dimension, right? So all that's left is 1 dimension that's perpendicular to both V and W. All right, and so this vector we call N. This vector N is the direction vector of the plane, but notice it does not live in the plane, right? So the direction vector of the plane, I wrote N because N also has another name. It's called a normal vector. So normal vector to the plane. And normal here is another word for perpendicular. So this means that this vector points in a direction that is perpendicular to the entire plane. So again, there's lots of different choices for this vector, right? For this vector N. This vector N has to be either pointing up or down, though, right? It could be pointing this way. As long as it's perpendicular to the whole plane, it could be moved around to be attached to any point. You can make it longer or shorter, right? As long as it doesn't get too short to just become the single point P, right? So in this case, we will almost always be, in this class, we will almost always be given this vector N, but this vector N, again, it's just like our direction vector for our line, has to be written in angled brackets so that we know it's an arrow, it's a vector, and its coordinates A, B, and C. These are going to be the direction of the arrow that is not in the plane, right? It's not in the plane. So I'll let you read about in the book and do the homework problems about this, but the idea here is that we only need one point that passes through the plane, or that the plane that lives in the plane, and a direction vector to describe a plane, which is the same amount of information we needed for the line, right? We needed at least one point and then the arrow, right? If we have 2 points, then we can make the arrow. But you could imagine if you have just one point here, like A, and then you have the direction vector V, you can just expand that vector and flip it around and fill out the whole line, right? So 1 point, 1 vector. That's all the information you need. Down here for a plane, we need the same amount of information, except the vector has to be a little more special, right? So we need a point in the plane, and we need a vector that actually points in a direction that's perpendicular to the plane. So that's very important, right? It's got to be perpendicular to the plane. But it's interesting, though, that you need the same amount of information to make the line and the plane in this scenario when you're thinking about these vectors. It's just that the vectors play very different roles in the two situations, right? In the line, the vector's in the exact direction of the line. For the plane, the vector's in the kind of the anti-direction, right? The direction that's not part of the plane.